Baik, kita mulai ya rekan-rekan sekalian. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore rekan-rekan mahasiswa sekalian dan juga Bapak Ibu dosen yang barangkali juga bergabung di sesi kelas hari ini. Jadi selamat datang kembali di perkuliahan pembelajaran mesin lanjut atau Advanced Machine Learning. Jadi ini adalah pertemuan ketiga dari perkuliahan pembelajaran mesin lanjut. Di pertemuan pertama, teman-teman sudah bertemu dengan Pak Novanto Yudhistira. Kemudian di pertemuan kedua lalu dengan Dr. Noman Naseer, dan hari ini kita juga akan bergabung kembali dengan Dr. Noman Naseer untuk membahas mengenai MLP dan Convolutional Neural Network. So before we start, I would like to say thank you very much for Dr. Noman Naseer for joining our classroom for the second time. So hopefully everyone enjoy this course. So today, Dr. Noman Naseer will give you a lecture about the MLP and Convolutional Neural Network, right? Is it right, Doctor?
That's true. That's true.
Okay. So that will be our topics today. So please, if you have any question during the lecture, just raise your hand or just open your mic and just interrupt Dr. Noman Naseer presentation. It will be okay. So we hope you guys have a lot of questions. It means that you really enjoy this course a lot. And one more information to all of the participants, we already invite you to our self-paced learning class in AWS Academy. So you can just join this course and just do anything related to the hands-on and so on. It's just an additional course. It's just enrichment. So you will not be charged for that. So it's totally free from us. So without further ado, let me introduce Dr. Noman Naseer. So for Dr. Noman, time is yours.
All right. Thank you very much. Could you please give me a feedback on how my voice is today?
Sorry, could you once again?
So is my voice clear and loud?
Okay, clear now.
Okay, great.
Okay.
All right. Thank you very much, my friend, for introducing me and giving me a chance to teach this course, actually. I just heard that you guys have got a chance to learn a self-paced machine learning course as well, and that too for free. Or that's a feat, actually. I mean, if you get something to learn for free, just grab it. So do go to that course and see what's happening. All right. So I hope my slides are shared now, and you can see my slides well.
Okay, already great.
Okay, great.
Yeah.
So as you know, we are doing a course on advanced machine learning, and it's a 3-in-1 course in which I'll be covering the theory part. And today I'll be talking about MLP and CNNs. MLPs and CNNs are different topics or two different topics which are embedded into one in this certain class. MLP actually stands for multi-layer perception, whereas CNNs are convolutional neural networks. MLP is a relatively older concept and is being used for some decades now. However, convolutional neural networks, CNNs, are a relatively new concept and recently have been used extensively for image classification. So let's start with the introduction of MLP first. So MLP, as I said, is multi-layer perceptron. And as you can see from the name, that it consists of multi-layers of perceptrons. Now, to go further into multi-layers of perceptrons, we need to know what a perceptron is. Once we understand what a perceptron is and how does it work, we shall be able to learn more about what the multi-layers of those perceptrons can do. So we'll just go to introduction, we'll go to some examples, and then we'll build our issue to multiple layer perceptrons. So a perceptron is actually a very simple algorithm, simplest form of neural network that is intended to perform binary classification. You know, binary classification is a two-class problem. Either something belongs to class 1 or class 2. Either it's a 0 or a 1. So the output is either 0 or a 1. The input, however, can be multiple, more than one, and those inputs are assigned some weights. So this is how a perceptron looks like. So in X, Y, and Z, we have inputs. These inputs are usually feature or feature vectors in form of vectors or the raw data, whatever that depends on how do we want to do classification. And then those inputs are assigned some weights and bias. Then we get the net sum of those and use an activation function to perform the output. So if we see this perceptron, essentially it is a single layered neural network and it consists of essentially four parts. One part is the input. The other part is the weight and bias. The third part is the net sum of those weights and biases. And the fourth part is output, which is actually received through the activation function. So if you read this line, perceptron is a single layered neural network which consists of four main parts: input values, weights and bias, net sum, and the activation function. Now we'll see how does it work. So the process, it starts with the inputs, of course. As you can see in next slide. Sorry, yeah, here it is. So the process begins by taking all the input values and multiplying those values by their weights. So you can see here, these x's are the input values, and we multiply these x by weights. So this is in vector form. If you see individually, you can see this perceptron in which we have some inputs like x1, x2, x3, and up to xn. We have same number of weights, W0, W1, and up to Wn. W0 is usually a constant, and W1 is the weight assigned to x1, W2 is the weight assigned to x2, and so on. We multiply the inputs with the weight and then sum those up cumulatively. Of course, we can add a DC shift or a bias, which is represented by B in here. So what we do is we uh, we take all input values, multiply them by their weights, and after that, all of those multiplied values are added together. We add them together to get the weighted sum. So we get a weighted sum. This weighted sum is then passed through an activation function. So usually a step activation function is used, and the reason is that in case of a perceptron, we do binary classification. So for a binary classification, we either require a 0 at output or a 1 at output. For that purpose, a step function is very ideal. However, in some cases, a nonlinear activation function can be used as well. So you can see this equation becomes this. So summation of all those multiplied and bias added weights, and then they pass through a phi, where phi is the activation function. This we can write in a matrix form as W transpose into X plus B, and this phi is the activation function. This activation function plays an integral role of ensuring the output is mapped between required values such as 0 and 1 in case of binary classification.
Sorry, Dr. Noman, your microphone is mute.
Oh, sorry for that.
Okay.
So weight of an input is indicative of the strength of the node. So this weight actually provides you the strength of this particular node. If this is a heavy weight or a more weight value, then we can say that the strength of this input is more. The value of this particular input has more weightage in decision making. If all the weights are equal, that means all the inputs have same weightage in making the output. So it all depends on the input and the weights. And what does the bias do? The bias actually gives the ability to shift the activation function curve either up or down. Bias usually gives a DC shift. This is also equivalent to an equation of a straight line where we say W is equal to mx plus c. M where is the slope and c is the y-intercept. So if you change the value of c, you get different, a DC shift along the y-axis. So that's actually what it does, the bias. So essentially, we can say that a perceptron is a linear binary classifier. Usually, we use this word for a perceptron as well, a linear binary classifier. So classification decision for a given observation is based on the value of linear combination of observation. You can see why is it called a linear binary classifier? Because the decision of the classifier is based on observations, which were actually inputs, and not only the observations, but the linear combination of the observations, which you can see in here. This provides the linear combination of all those inputs and their weights. Therefore, this falls into a category of a linear binary classifier. This is what a single perceptron can do. Okay. Well, the history of perceptron we discussed in the last class as well. It was Rosenblatt who first basically presented the idea of a perceptron. In fact, he was given a research funding and he developed a hardware of a perceptron. He made this machine which he called Mark I perceptron, and this machine could actually make binary decisions based on provided inputs, and the weights were set. This was not a self-learning algorithm, the weights were preset, but this inventor, he popularized this device, this idea as a device rather than an algorithm. So it first entered the world as a hardware, and it was called Mark I Perceptron. You can see, because at that time of the era, there was no, solid state electronics. So everything was, semiconductor electronics. So everything was based on electrical devices or even electromechanical devices. Hmm. So someone of you is not muted, and we can hear him sneezing. Let me mute. Okay, done. So this is how the first perceptron looked like. Well, what were the issues with the single layer perceptron? Well, the issues of the single layer perceptron were highlighted by Min in 1969. And we will build up to that issue using the following example. Well, this person built a single layer perceptron. Therefore, it was a shallow neural network. We cannot call it a deep neural network. It's just a single layer perceptron. It's a single layer neural network. Now, this prevents his perceptron from performing nonlinear classification. It was good for the data that is linearly separable, but the data which is not linearly separable, it cannot perform classification for such data. And that was the major issue with the single layer perceptron. Well, let's see what it can do with the example of logical gates. You have you have studied these gates back in your 11th, 12th grades and engineering classes as well, or the undergraduate. You see, if you have two input values as A and B, and you have to take the AND, OR, and NOT. So AND and OR, both the gates, both the logical operators require two inputs. but not requires a single input. So can we build a system which can implement AND or and NOT gates using Perceptron? Well, let's see. So just for a revision, I mean, you might know in case of an AND gate, if both the inputs are false or zero, we get a zero. If one of the inputs is false or zero, we will get again a zero. If both the inputs are true or one, only then we will get a one or true. It's exactly the opposite in case of OR gate, in which we will get a false only if both the inputs are false or zero. Otherwise, even either one of the inputs is one, we will get the one at the output. And if both are true, we get the true at the output as well. NOT is basically an inverter. If you get a false, it will invert it to true. If it's a false, it will convert it to true. If it's true, it will invert it to false. So let's try to implement all these three operators using a single layered perceptron. And let's see what are the limitations of these single layered perceptrons. Let's first focus on a NOT gate. As I just told you, NOT x is a one variable function. You don't require two inputs. You will have only one input at one time. So it's a logical function. Remember, it's a logical function. So both inputs and outputs can just have two values. It can possibly have a value of 0 and 1. So it can have two states only, no third state allowed. So therefore, the unit step function should be a good activation function for our case. We can implement the NOT gate using a perceptron which has one input and one output and one activation function. We do not need, uh, you know, two inputs. It's just a one variable function, so we need one input. Similarly, the activation function could be a unit step function, which gives either a 0 at the output or a 1 at output. So this is how the output would look like. The y should be equal to the activation function, which is unit step function in our case, w into x plus b. Now the issue is, can we find the values of w and b such that this gate is implemented or the NOT function is implemented? Of course, we can do it. We can have multiple values for which this gate is implemented. For example, one such value is w is equal to -1 and b is equal to 0.5. If we set these two values, we see that if input is 0, input is x, output is y. If input is 0, we get 0 into -1 because we have set w is equal to -1 plus 0.5, which is our bias. So y is equal to activation function into 0.5. Now the activation function is a step input, which means it would be great, it would return greater than, it would return 1 if the value is positive or greater than 0. This is a greater than 0 value, so it would return 1 at the output. So what was given at the input? 0. What did we get at the output? 1. So this satisfies the NOT gate operation. So using a single perceptron, we can very easily implement a NOT gate. Similarly, if we provide 1 at the input, what will happen? If you provide 1 at the input, activation function is same, w is -1, x now is 1, so the input is 1, and bias is again 0.5. So -1 into 1 is -1 plus 0.5, which returns -0.5. Now this value is negative. So a unit step activation function returns 0 for a negative value. So for a value of input 1, output returned is 0, which means that the input is inverted at the output, or we have implemented the NOT gate. So using a single layer perceptron, we can easily implement the not operation. So for not of input 0, we get 1, and not for input 1, we get a 0. I hope this thing is clear. If it's not clear, you can ask me now, because the next and an or, an XOR, etc. will be built on these gates. I hope this is clear. I mean, I'll just repeat quickly once again. So this is what we do in a single layer perceptron. We add all the weights, but we have just one input, so we don't have to add other things. So we have one input. We set the value of W and B such that at output, using this activation function, we get the inverse of what we want to get. You know, so for a 0 input, we should get 1, and for 1 input, we should get a 0. So if we set W is -1 and B 0.5, then we can see for an input 0, at the output we get 1, and for input 1, at the output we get a 0. So essentially, X is inverted at the output. So we have implemented the NOT gate using a single layer perceptron. Now this was a very easy function in which we just had one variable. Let's see what happens in the case of AND gate. For AND gate, we must have two variables or two inputs. We cannot take AND of just a single variable. We should have two variables like AND x1, x2, and the output should be as per this. So can we implement it? Let's see. Now the equation would become y is equal to the activation function multiplied by w1 into x1 plus w2 into x2 plus the bias. Now this is x1, the first input. This will be multiplied with w1, the first weight. And the second input, x2, will be multiplied by the second weight. And we'll add them up and we'll add a bias. And then output should be as per this activation function. Now again, since we have the binary output, so we can use a unit step function. So this activation function will again be a unit step function. Now in this case, we need to determine three values like W1, W2, and B. So the question is, can we set such values of W1, W2, and B such that at the Y gives us the AND of X1 and X2? Well, of course, we can do that. The answer is yes. For example, we can have multiple values, by the way. For example, W1 is 1, W2 is set to be 1, and B, the bias, is set to be -1.5. Now, what happens when both of these are 0? When x1 and x2 both are 0, we should get a 0 at the output. That's what the AND logic says. So let's see. So when this is 0, it's multiplied by 1, you get a 0. This is 1 because W2 was 1, multiplied by 0, x2, which is, we get a 0. Minus 1.5 because the bias is minus 1.5. So y should be equal to activation function minus 1.5. So both these W1 into x1 and W2 into x2 become 0. So we only have a bias inside the bracket, which is minus 1.5. So the activation function of minus 1.5 or the step function of minus 1.5 will give you a 0 because it's a negative value, and step function for a negative value is always 0. It's 1 for only for positive values. So the first case is verified. If x1 is 0 and x2 is 0, we get 0 at the output, and hence we can say that the AND logic is implemented if we see the first case. Now for the second case, when x1 is 0 and x2 is 1, what happens is that this side of the equation becomes 0 because x1 is 0. But this side of equation becomes 1 because x2 is 1. So 1 multiplied by 1 is 1. But still we have a minus 1.5 bias. So this becomes minus 0.5. Again, the step function for minus 0.5 gives you a 0 value because it's a negative. So for x1 0, x2 1, it gives you a 0 value, which is verified for an OR AND logic. Now same goes for when x1 is 1 and x2 is 0. Again, this side becomes 1, but this side becomes 0, and this is minus 1.5. So eventually you have minus 0.5 in the activation function. So activation function will return you a 0. The only case when the output will be 1 should be the case when x1 and x2 both are 1, or we can say both are true. So when x1 is 1 and x2 is 1, what happens is that we get 1 in here, 1 in here, and minus 1.5 in here. So we get 2 minus 1.5, which is 0.5. Now this is a positive value. Because this is a positive value, the step function will return us a 1. So verified that x1 is 1, x2 is 1 will yield output of 1, which is the case for AND logic. And you can implement the AND logic very easily using a single layer perceptron. You can see that we have proven AND of 0, 0 is 0, AND of 0, 1 is 0, AND of 1, 0 is 0, and AND of 1, 1 is 1. So NOT logic can be implemented very easily using a single layer perceptron. AND logic can be implemented very easily using a single layer perceptron. Can we implement OR logic in a similar way for a single layer perceptron? Let's see. Again, the OR logic function is also a two variable function. We need to have two inputs. And again, it's a binary function for both inputs and outputs. So a unit step function would do the work. Again, the equation should be the same. Output is equal to the activation function, which is a unit step function. W1 into X1 plus W2 into X2 plus B, which is the bias. Can we have such values of W1, W2, and B for which an OR gate is satisfied? Of course, we can have multiple such values. One such example is this. If we set the value of W1 to 1 and value of W2 to 1 and B to 0.5, we can satisfy this and we can verify this as well. If we have x1 is equal to 0 and x2 is equal to 0, what happens is that both of these are 0. So both of these are multiplied by W1 and W2 and we get 0. But the bias is minus 0.5. So activation function gets minus 0.5. So for minus 0.5, it will return a 0. Well, there's a mistake in here. These should be ones, not zeros. So we have a problem here. These should not be zeros. These should be ones. My bad. Okay, let's go to it. So what happens is that when x1 is 0 and x2 is 1, this thing becomes 0 and this thing becomes 1. So 1 minus 0.5 is 0.5, which is positive. Now this is positive, so y should be 1. As in the case of OR logic, it should not be 0. Similarly, if x1 is 1 and x2 is 0, this becomes 1, this becomes 0, and we have minus 0.5 in here. So 1 minus 0.5 gives you a 0.5, and it is positive, so a unit step function will give us a 1. Similarly, for both values of 1, you will get 2 in here, 1 plus 1, minus 0.5 will return us 1.5, which is a positive number, so we get a 1. So eventually we see that OR for a 0, 0 is 0, OR for a 0, 1 is 1, and OR for a 1, 0 is 1, and OR for a 1, 1 is 1. So what happens is that we have implemented an OR gate very easily using a single layer perceptron. Just a moment, please. Okay. So I hope the things are clear till now. So we can implement and, or, and not using a single layer perceptron. Can we implement XOR? Now, this was the problem that was basically proposed in their paper in 1969 by Minsky and Pepper. They were very critical of the success of single layer perceptron. They said that a lot has been claimed for a single layer perceptron or a single perceptron, but it's not as versatile as it has been presented. So they were very skeptical of it and they presented the XOR problem. This XOR problem is very famous problem, and it says, XOR is basically exclusive OR, which actually means that it will return uh, a true or a one value if if both the inputs are not same, or both inputs are not same. So if both inputs are same, which means if both are 0, it will return a 0. If both inputs are 1, it will return a 0. But if both inputs are different, like it's a 0, it's a 1, it's a 1, it's a 0, then only it will return a 1. Can we implement this using a single layer perceptron? Well, let's see. It's an XOR problem. It's a two variable problem. We have two variables, so equation is the same. We can use a step unit function as well. However, when we try to find out the values of W1, W2, and B, we cannot find any values of W1, W2, and B for which this equation or this output is satisfied. Well, the reason is they do not exist. No such values exist for which this is satisfied, because XOR problem is not linearly separable. Linearly separable are those things which plotted on a 2D plane can be separated by a single line, but this problem cannot be separated by a single line. Therefore, a single perceptron or a single layer neural network or a perceptron fails in XOR problem, which apparently is a very simple problem. But a perceptron cannot solve this problem. So we have no option but to go for multi-layer perceptrons. So let's see how we do that. Well, multi-layer perceptrons are a deep artificial neural networks. They're composed of more than one perceptron. They have an input layer to receive the signal. They have an output layer that makes the decision. And in between, they have more than one perceptrons which actually do the actual computations. Now, except for the input node, each of the node of the neuron, each node is a neuron that uses a nonlinear activation function. This nonlinear activation function can be used just to make sure that the data is linearly separable. Or it works on a data which is even not linearly separable. So MLP utilizes usually the backpropagation algorithm, which is a supervised learning approach or technique for training. On backpropagation is a very popular method in MLP, and there would be a specific lecture. I guess there would be a whole class of lecture that Professor Yudi will cover on backpropagation and manual calculations for backpropagation. You'll do that in this course. So it's multi-layer perceptron has multiple layers and nonlinear activation function. This actually distinguishes the multi-layer perceptrons from a linear perceptron or a single perceptron. Also, it can distinguish the data that is not linearly separable. So let's try to implement the XOR problem using a multi-layer perceptron. Now, the single perceptron with a unit function can implement each of the fundamental logics and, or, and not. And these are fundamental logics, and these are called fundamental because you can implement any complex function, any complex logical function using the combination of these three. So we can infer that if we appropriately connect these three perceptrons we just built, we can implement any logical function. So how do we do that? We do it like this. So it comes out that an XOR of x1 and x2 is equal to AND of this function and this function, where this is an OR gate and this is an AND of the two inputs inverted. So we can implement XOR like this. You can verify this using your digital logic as well. So how can we implement this? We can implement this using this perceptron. Now this is multi-layered perceptron. You have more than one perceptron in here. You have this perceptron, you have this one and this one. So you implement an AND of these two functions and invert it using this perceptron. You also implement an OR of these two functions and give it to this perceptron's input. So in actual, we have 1, 2, 3, 4 perceptrons in here, which are using same x1 and x2 output inputs, and we get a y as the output. So in this way, we can implement the XOR problem using multiple layers of perceptrons, and this is so-called multi-layer perceptron. Of course, this is a very simple example, and more complex than nonlinear functions, we use back propagation to adjust the weights and other things which you'll learn in this course. So multi-layer perceptrons have shown that they're capable of approximating an XOR problem as well as many other nonlinear functions. So I hope that the idea of perceptrons and why do perceptrons fail and why do we need to have more perceptrons or more layers of perceptrons to get our nonlinear estimation of nonlinear functions is clear. I hope this idea is clear. When you learn about the backpropagation, probably you'll do more on this as well. Okay, so this part is the end of the MLP part, the multi-layer perceptron part, and now we'll move to the basics of the convolutional neural networks. Okay, just a moment. I'll just drink a glass of water and then I'll come back.
Okay, maybe during your break, I can ask the student whether they have a question or not.
Sure,
Okay,
sure.
Oke, ada pertanyaan mungkin dari teman-teman partisipan. Saya menyebutnya partisipan karena ada mahasiswa dan juga ada dosen dan dari luar juga ya. Monggo, kalau ada pertanyaan dari rekan-rekan sekalian terkait dengan metode MLP atau mungkin ada bagian yang tadi diterangkan oleh Dr. Noman kemudian Anda tidak paham, Anda bisa menanyakan ya. Kalau mungkin sungkan menanyakan dalam bahasa Inggris, bisa ditanyakan dengan bahasa Indonesia kemudian saya translasikan. Monggo silakan teman-teman mahasiswa barangkali. So, is there any question? Just raise your hand, angkat tangan. Oke, kemudian bisa dibuka mic-nya. Oke, ya ada satu pertanyaan. Silakan Mas Jagat.
Oke, sebelumnya izin bertanya Pak kepada Dr. Noman. Untuk fungsi aktivasi dalam otak manusia itu diibaratkan sebagai apa ya? Karena kalau neuron di otak manusia itu diibaratkan sebagai node dan akson di otak manusia itu diibaratkan sebagai wave. Untuk fungsi aktivasi itu sendiri diibaratkan seperti apa ya? Terima kasih Pak.
Oh, okay. So I will translate. So we have one question, Dr. Noman.
Okay, it's really pleasing
we have
to
one
see
question
a raised hand.
About the how can I say modeling about the human brain. So okay. In case of the artificial neural network, we have a node and we have a weight. So the weight will be in the human neural system will be the axon, right? And the node will be the neural cell. Maybe I'm not so precise about that.
Okay.
So what about the activation function? What will be the similar things in human brain that makes up of the activation function?
That's an absolutely amazing question, actually.
Yeah.
And the answer is that we don't know.
Okay.
Well, what happens is that, the dendrites, they get the input. And there's a cell body which has a nucleus. Those activation, those inputs go through the dendrite and travel through axons to the axon terminals, which gives the output. The decision making is based on very complex model inside the brain that differs for every human being. That is based on the training of that human being. Now, the example is that if I give similar situation to two different people, both those different people might take a different decision. That happens, right? We give a similar situation to different people and they make a different decision out of it. The reason is that the activation function, because of their training, it's a heuristic kind of activation function, differs and it's primarily based on their experiences. For example, there's a situation in which someone will take an aggressive action, whereas the other one will not take an aggressive action. That decision or that activation of decision is based primarily on what he has learned in life. What has he seen? How has he managed his temper throughout his life through his learning? So that actually is what happens inside the brain. So we do have an activation function going on in the nucleus, but that activation function has not been modeled yet. There are heuristical approaches that have been made to estimate that activation function, but that differs for each and every human being and is primarily based on the history or the learning of that particular human being. I hope this is the answer to your question.
Okay, so it means that the activation function has a role to decide something, right? Based on the input of the data or input of the, in the case of the human brain, it will be the input of the maybe a sensoric things from the human being, right?
Absolutely.
Yeah.
You see,
Okay.
in here, in this photo, you can see that the primary task of the activation function is to give the output based on what he gets as the weighted sum. So this activation function will give the output, which will be the decision in our case. So that's how it happens. So even in the human brains, there are activation function. Of course, we don't have a step activation function. It's very different than this, but this will give us the decision. It's inside the nucleus of a human brain, of a human cell. Neuron.
Okay, thank you very much for your kind answer. Mas Jagat sudah menjawab pertanyaan dari sudah?
Sudah Pak, terima kasih.
Okay, he said thank you very much for your answer.
You're most welcome, and thank you for breaking the ice. You're the first one to ask the question.
Okay.
So I'm too happy to hear a question, and too happy to hear the voice of Indonesian students.
Oh. Okay. Ada pertanyaan lain dari teman-teman? Is there another question? Oh, raise hand. Okay, that would be great.
That's great.
Two students.
That's great.
Okay. So, Mas Michael, Stephen Louis. So. You can directly use the English or just in Indonesia is okay. I will translate it. Yeah.
Okay, Dr. Noman, I want to ask about something. So the weak thing about single neuron is that it cannot do nonlinear classification. So there is classification called support vector machine. So one of the function is called kernel trick, and that can classificate nonlinear problem using one function, such as radial basis function. So why not we use kernel trick in a single perceptron instead of
Excellent. Yeah,
multi-layer?
good. I got your question.
A quite technical option. So
yeah, and that's a good question as well.
Okay.
So, well, the question, if I understand correctly, is that in the problem with a perceptron is that it can do binary classification, and it cannot work on the data which is not linearly separable, or which in case we need a nonlinear classification, non-linear function. And that we can do using support vector machines, using the kernel trick. We can use RBF kernels, and there are many kind of kernels that we can use. Of course, we can do that. Of course, at the output, we can do that. However, the network made through that thing won't be a single perceptron in itself. That would be using a single perceptron as the input to something in which you can use a kernel function and predict the values. For example, SVM or any other thing. Herein, in this particular lecture, I'm trying to tell what a perceptron originally is. A perceptron originally is this thing that I told you. It does not have a kernel trick. Of course, we can put, which could be an addition to it, and people have done that afterwards and made some other models as well. But to build up the idea of perceptron and why do we need multi-layer perceptrons, this was the basis.
Okay. So it's technically it's quite possible to integrate something like a SVM kernel trick into this single layer perceptron. But to build the understanding of the multi-layer perceptron, we need to understand the single layer perceptron first, right?
True. It is very much possible, and people have done it in research. Actually, already they have done it.
Okay. So already answered?
Yes, thank you very much.
Okay, thank you very much. Okay, so the second question, the next question, actually the third question from Miss Latansa Nuri. So, yeah.
Okay, Dr. Noman, I want to ask, in the Macolat bits, we can get value of W1, W2, and B with manually test a random value. Is that similar in the Perceptron model, Dr. Noman?
Okay, so what I get from this question is that in case of a single layer perceptron or a single perceptron, we put the values of W1 and B1 manually. Is it the case in the multi-layer perceptrons as well? So no, it's not the case. What we do usually is we use a back propagation technique to update the weights. Even in case of single, we cannot do that. We don't do that. That was not how it was developed, the perceptron, in which we cannot adjust the weight. So we can say that it cannot learn on its own. The single layer cannot learn on its own, but the multi-layer perceptrons can learn on their own. They can update the weights using the technique which is called the back propagation. And that technique we will cover in some other lecture. Professor Yudi will do that, and we will do manual calculations of those updating of weights as well using the back propagation. So in case of multi-layer perceptron, we don't have to manually set the values. It can automatically adjust the weights using different techniques. One of the most famous of those is the back propagation. I hope this is the answer.
Okay, already answered, Mbak Latansa?
It's also same with to get the p-value, Dr. Noman.
Is it the same to get the p-value with to get the w value? I think it's the same.
You see, yes, but it's important to understand that w value is really important. B value just gives you a bias or a DC shift in the activation. So B value can be manually set, depending on your what kind of output you want to get and what kind of activation function you have. B value can be manually set, and you might not you might not. I don't say always, but you might not have to set it all the time.
Mhm.
But weights are very important. Weights are important because they decide the strength of a node, and depending on the strength of the node, the output is made. So B value is a single value
Mhm.
and it's not very important. It just gives you a DC offset.
Okay.
But W's are really important.
Or in my understanding, we can we just multiply B with the one value maybe?
Yes, we can do that.
Uh-huh,
In case
uh-huh.
when it's not really important in the case of output, you can simply multiply it by 1.
Oke, oke, that will be great. Sudah menjawab Mbak Latansa? Sudah ya?
Sudah, Pak.
Okay,
Makasih.
thank you. Okay, thank you very much. She said thank you very much.
Welcome.
Okay, and maybe last question for this session. Maybe we can we have more question in the later. So please, Mas Reza Setiawan.
Excuse me, sir. I would like to ask about the history earlier about Rosenblatt. In other lectures, I learned that the first neural network is McCulloch bits instead. So I'm kind of confused in the difference between Rosenblatt and McCulloch bits.
McCulloch and Rosenblatt. Yeah.
Okay,
Yes.
so McCulloch actually presented the model of a neuron. It did not incorporated the the different weights and the decision and activation functions, etc. A perceptron was the name given by the second guy, the Rosenblatt. It was given by him, and it actually incorporated the weights, different inputs, and the activation functions, etc. In the first one, McCulloch, he just presented the model, the mathematical model of how a neuron would look like when translated to maths.
Okay. So it's quite a bit different, right, between the what
Yes,
McCulloch
yes.
proposed
I
and
mean,
what Rosenblatt.
yeah, I mean, the bases were given by McCulloch. Rosenblatt's work was based on basically McCulloch's work, because for the first time, the neuronal modeling or the mathematical model of how a neuron would look like was done by McCulloch. But based on that, the inputs, their weightage, the weighted sums, and decision making, that was done by the Rosenblatt. In fact, that was made. A hardware was made, a machine was made that could do that.
Okay, so already answer, Mas Riza?
Yes, thank you very much, sir.
Okay, you're welcome. So can we proceed to the CNN, Dr. Noman?
Sure. We can proceed.
So
It was really nice to hear your voices. It was really nice to get questions. I mean, it's always enjoyable to get the feedback and questions. So from the quality of questions, the professor learns actually that what kind of confusions, what kind of question, and what kind of learning the students are having.
Yeah.
And by the way, this Sunday, I was hiking in the Margala Hills, and I met some Indonesian students. And yeah, there were
Pakistan?
6. Yeah,
Really?
in Pakistan, there were 6
Oh.
of them. 6 of them,
Uh-huh.
all girls, and 6 of them. And when I told them that I'm teaching in University of Brawijaya as well, they were really surprised. And one of them actually belonged to Malang. And she also told me that there's a very famous hiking and trekking place, Mount Somero or something like that.
Semeru is the highest mountain in Java Island.
I see. So she said you must go there the next time you visit Patna.
Okay.
I said, oh, I'll
Sure,
have to
sure.
take 2 or 3 days, but yeah. So they were actually doing a course on Islamic studies from the International Islamic University in Islamabad. So it was really pleasing to know that, and they were quite happy and surprised to see that a professor from Pakistan was teaching a course in UP as well. It was a good experience.
Okay.
So anyway, nice to have your question.
Yeah,
and
yeah.
we'll just move forward to the
Okay.
CNNs. Okay, so we'll go to the definition of CNNs first. Convolutional neural networks are the neural networks that has one or more convolutional layers. Now, what is a convolutional layer? That I'll tell you. What actually is convolution in terms of image processing? What we call is we slide a filter over the input, and we'll see some examples of it. This concept was first presented in 1998, which is quite new. So 1998 is not many years ago. So it's quite a new concept. And then, convolution concept is old, but convolution for classification of digital images was presented in 1998. So a convolutional neural network takes some inputs. It has a convolutional layer. Sorry, then it has pooling layer. We'll study about that as well. Then we have an activation function as well. And then we have, the fully connected layers, loss function, and we get the results. We'll discuss all these things one by one. So, before convolutional neural networks, what we used to do was we used to have features directly from the images or the pixel values of the images. And we used to get those features and feed those features to classifiers like a linear discriminant analysis, logistic regression, KNN, SVM, etc. So in that case, the problem was that pixel level values were used as features. And so, for example, we have an image of 28 by 28. In this case, we'll have 784 features, which are the pixel values. Now, these are lots of features. And if we have a huge image, then the features will be a lot more. And this way, what we do is we lose the spatial interaction between the pixels because we're using individual pixel values. So the interaction between different pixels or similarities between them is lost, and we don't use that. That was one of the more drawbacks of using conventional or machine learning algorithms or pixel value level values as features. You see, one could still manually pick up the features out of the pool. However, that was a tiresome process, and that's exactly what convolutional layers do. So convolutional layer uses information from the adjacent pixels and downsamples usually the image into features. And those features are then pooled and, if required, again convoluted, and then prediction is based on the features from the convolutional layers. Let's see, how do the convolutional layers work? What we do is we use multiple convolutional filters. So there are some very well-known filters or kernels that we call that are run over the image to compute the dot product. And those dot products are all added of the to get a final value. Each filter extracts different features from an image. So if we have two filters, we'll get two different feature values from an image. And how do we do that? We learn it using an example. So you see, let's say we have this image whose original size is 5. You can see that the original size of this square matrix, what you call, is 5. 1, 2, 3, 4, 5. And we use a filter, which is a kernel filter. It has a size of 3 by 3, so it has a size 3. So what we do is we perform element-wise multiplication between the image pixels and that match the value of the filter and the kernel itself and sum them up. This provides us a single value for the feature cell. So what we do is we put this yellow filter, or sometimes we call it a mask as well, over this, and we multiply 1 with 2, 4 with 2, 9 with 3. So what we do is, let me make things clear for you using this annotation. So these two guys are multiplied, these two guys are multiplied, these two guys are multiplied, this is multiplied by this is multiplied by this 4 is multiplied by this one by this 2, this one by this -5, and this 2 by -1, and we add all all of them. The result that we get is a single value, and that single value we put in this. So you can see 2 into 1 plus 4 into 2 and so on and so forth. We get 51. This 51 we place in here. Then what we do is we just move this mask one step ahead. We move this mask one step ahead such that it now goes here in these three. So we move this mask one step this side. So now it covers these. And we again compute the same thing and put the result in here. Then we move it one more step such that it now goes here. And we put the result of this in the third one. Then we move it here, then here, and then here, and so on. So we keep moving it one step ahead and put the results in here. So let's see, in the next slide, I've shown it like this. So the result of this mask is convolved by taking the dot product and put here. The result of this mask is convolved by taking the dot product and put here. And so on, the result of last mask or kernel or this would be put here. So in this way, the original image has been reduced to this. So this is original image. This is the kernel or the filter. We convolve these two. We call it convolution, and we get the feature vector as this. Now this feature vector contains the information of adjacent pixels, because all of them have been added by multiplying it with a mask. These masks are usually well-known masks. We do research on making these masks better, but I mean the research in this direction is quite saturated, and we have some known masks that we put over the image and calculate the features. Now you can see the dimensionality has been reduced. Previously, we had 5 cross 5, which is 25 features. Now we have just 9. And those features do have information of the adjacent pixels as well. So that's why it is very important to have a convolutional layers. And sorry. And that way we reduce the dimensionality and preserve the information of the adjacent pixels as well. So if we see the above example, what we do is we slide the kernel by 1 pixel. This actually is called a stride. You know, whenever you talk about the convolutional layers, you will hear a word called stride. If we had skipped one layer, one column, and had convolved in here, then we would have said that we did not cover all of them, and when we skipped one, and stride would have been 2. But if we slide by the kernel by just 1 pixel and we don't skip any pixels or any column of pixels, then we call it a stride 1. Of course, we can have the kernels move by different stride values to extract different kind of features. We can extract different features if the stride value is 2. If the stride value is 3, we can have different features. So we can have all those features and we can use them for classification. Now, you know, the amount of stride we choose affects the size of the feature extracted. Now that's very evident, and I'll show you how. The equation to calculate the size of features for a particular kernel size is this. You know, feature size is equal to the image size minus the kernel size, whole divided by the stride, and whole is added into 1. For example, if we see our example, in this we have image size of 5, kernel size of 3, and stride of 1. So we get a 3 by 3. So let's see what happens when you put in this example. So image size is 5, kernel size is 3. We get 2 from here. Stride is 1, so 2 divided by 1 is 2 plus 1, we get a 3. And that's our feature size. So this is image, this is filter or kernel, and this is the feature. So if you have 5, this is 3, and stride 1 is used, then we get a feature of 3 by 3. What happens when we change the stride size? Now, for example, we use stride 2. If we use stride 2, the kernel of 3 on 3 by 3 on the image of 5 by 5, what happens is the feature size becomes 2. So 5 minus 3 is 2 divided by 2 becomes 1. 1 plus 1 is 2. And how does it work? I'll show you. So what we do is first we move in here. When we get the results, we put those here. Then we skip this part and we move it here. So we skipped this part, so the stride is 2. We did not move by 1 pixel, we moved by 2 pixels. So the stride is 2. Then we go down and put the mask here and then put the mask here. So this goes to this goes to this, and this goes to this. So eventually we have a 2 cross 2 or a 2 size feature, which is evident from the equation as well, that if we use a stride 2, we will get the feature of size 2. I hope this is not too confusing and this is clear. So if the stride is 1, you move by 1 pixel, you get more feature values. If the stride is 2, you move by 2 pixels, you get less feature values. So this is how stride works in convolution. Then there can be instances in which we want our features to be of the same size as the input image. So what we do is we want to do convolution as well, and we want the feature to be of same size as the original image. What do we do? In that case, we do what we call padding. Now, padding is also a word that you will hear a lot when it comes to convolutional neural networks or the convolving layers. Now, padding is the technique of adding zeros around the margin of the image to increase its dimensionality. Now, this image was 5 cross 5, but this image we have added zeros around the margins, and the image has now become 7 cross 7. So what happens is padding allows us to emphasize the border pixels, and it uses in order to lose less information. So we have this 5 cross 5 image, which is padded to 7 cross 7 by adding additional zeros, and we apply a 3 cross 3 filter. When we convolve it, we get a 5 cross 5 feature vector, which is actually also the original size of our image, which was 5 by 5. So if we want the feature to be the same size as the input image, we can use padding technique. If we add another layer of zeros in here, then we would say the padding is 2, and the image size would become 9 cross 9, or size would become 9. So in case of padding, when we have paddings and strides both together in an image, the formula to calculate the feature size goes something like this. It has to be image size plus 2 multiplied by the padding size minus kernel size whole divided by the stride, and this all is added by 1. We can verify this example. So in this example, we had a feature size of 5. 2 was the padding. No, sorry, 2 is a constant. Padding was 1, and minus 3, which was the kernel size. And from here, we get 4 and plus 1, we get a 5. Just a moment. Oh, yes. So this is 2. So it's 7. 7 minus 3 is 4. 4 divided by 1 is 4. And plus 1 is 5. Yeah, that's right. So 5 is the size that eventually we get. So this formula is used when we have padding as well as stride as well in the image. This is an animated representation of how yeah. In this one, you can see that this is the input image and this is the output image. And you can see the animation, right? Animation moving. So image size is 5. The kernel size, the moving here in orange, is 3. Stride is 1 because we are not missing any pixels in between. Padding is 0 because nothing is added on the sides. So the output size would be 3. And in this particular case, we have image size of 5, but we have a kernel size of 3 again, but there's a stride of 2. You know, we are missing one particular, we're having a stride of 2. We're not moving by 1 pixel. So in this case, we'll have an output of 2, and we can verify this using the formula as well. In this one, we can see that we have same image size of 5, but a padding of 1 is done. So it becomes 7 cross 7. We have the kernel of 3, the stride of 1, and of course the output would be 5, as we saw in the previous example as well. Now what happens when we have a stride of 2 in such case, when we have a padding of 1 as well? So this is what happens. So we have an image of 5, we have padded it to 7, 3 is the filter, we have a stride of 2 and padding of 1, so the output would be size 3. We can also verify this using the formula. So that's actually how the convolutional layer works. So convolutional layer gives us a feature vector, which is in this form, and we can play with the dimensions of feature vector by playing with the padding size, stride size, or even the filter. And then comes the pooling layer. Once we have the features, what we do is we try to reduce the spatial size of the convolved features for dimensionality reduction. It helps also us to reduce the overfitting, which can be provided by abstracted representation of the spatial features. So it is sample-based discretization process, and it is actually similar to convolving or the convolutional layer, except for the fact that there is no filter that is applied to it, and also there's no dot product between the input layers. Instead, we just take the max of the region from the input overlapped by the kernel. So what we do is we do this. For example, if this is the kernel of size 2 having stride 1, so we will just take the maximum value out of these 4, which happens to be 59. Then if we move it here in the next one, the value would be, the maximum value would be 66. In the next one, the value would again be 66. In the next one, the value would be, the maximum value would be 43, and so on and so forth. That's how we make it. You can see it here, 59, 66, 66, and 43. Then it will come here, and the maximum value out of these 4 is 51. We put 51. Then it will go here. The maximum value out of these is 66. Again, it gets to 66. It comes here. What is the maximum value now? 101. 101. And so on and so forth. So that's how we pool the features. Now you see the dimensionality has been reduced, and these are called max pooled features. The dimensionality of these features was 5 cross 5, and the dimensionality of this one is actually 4 cross 4. If you use, more stride or more, more size of kernel, then we'll have even further reduced dimensionality of the feature. So this layer is actually called pooling layer. Max pooling is not the only way of pooling. There are certain other ways of pooling as well. For example, one of them is called average pooling. In average pooling, what we do is we don't take the maximum of these four, we take the average value of these four. So in this one, the stride is 2. So for maximum pooling, it would return 9 because 9 is the maximum value out of these four. But in the average pooling, it will return 9 plus 3, which is 12, 12 plus 4, which is 16, 16 plus 0, which is 16, 16 divided by 4, which is 4. So the average value of these fours is 4, and that will go here. And same goes for this one. The average value of these is also 4. The average value of these is 5. And the average value of these is 6. So in maximum pooling, max pooling, we take the maximum values. In average pooling, we take the average values. Okay, so there are different ways of pooling. And then lately, I have seen some people using stochastic pooling as well. So stochastic pooling for regularization of CNN is done by replacing the conventional deterministic pooling operations with a stochastic procedure in which we randomly pick the activation within each pooling region according to a multinomial distribution given by the activities within the pooling region. So this is, I mean, in latest research, I see that this has been used very regularly as well. Now, once the pooling is done, then we apply an activation function. Now, this activation function could be the hyperbolic tangent or the ReLU or leaky or many other. However, it has been shown that ReLU is the most used activation function for many kinds of neural networks using CNN because of its linear behavior, and it's easy to train, and it often yields better performances. And I explained in the last class as well, ReLU actually stands for rectified linear unit. It's a rectified function, which means it gives 1 when the input is greater than the value of x is greater than 0, and returns 0 when it's less than 0. And it's a linear for greater than 0 with a slope of unit or slope of 1. The good news is, I mean, people often ask me whether you apply max pooling before ReLU or after ReLU. The good news is that max pool is commutative on ReLU. So either you apply max pool before ReLU or after ReLU. In both cases, you get the same result. So conventionally, they do apply it beforehand, but you can apply after that as well, no problem. So different activation functions can be used. After activation functions, we have fully connected layers. Now in CNNs, the fully connected layers are the input layer nodes that are connected to every node in the second layer. So if this node is connected to every other node in the second layer, and in this input every other node in the second layer, and so on, then we call them the fully connected layers. Now adding a fully connected layer helps learn the nonlinear combinations of high level features outputted by the convolutional layers. So the nonlinear combination of the features that was outputted by the convolutional layers is understood, is aided, and so these layers help them in understanding those features. So usually activation function and dropout layers are used between the two consecutive fully connected layers to introduce nonlinearity and to reduce the overfitting respectively. At the last fully connected layer, we choose output based on our application. If we have a binary classification, we use the output based on the last. We choose output at the last fully connected layer based on our application. So it goes like this: we have input, we have convolutional layer, we have a pooling layer, we have an activation function, which could be before or after pooling. And then we have fully connected layers. And after that, we get our results. But, we can also have a dropout layer in between. Now, dropout is a regularization technique that is used to reduce overfitting on neural networks. So usually, deep learning models use dropout on fully connected layers, but it is also possible to use dropout after max pooling layers. So we can use them on fully connected layers as well, but we can use on the max pooling layers as well, creating image noise augmentation. So dropout randomly zeros some of the connected layers of the input tensor with probability P using samples from Bernoulli distribution. This is one of the way of regularization of the which actually reduces the risk of overfitting on the neural networks. Okay. And then at the end, we have the loss functions. The loss function is a method of evaluating how well a model models the dataset. The loss function will output a higher number if the predictions are off the actual target values, whereas otherwise it will output a lower number. So if the loss function is high, the accuracy is low. If the loss function is low, the accuracy is high. For multi-class classification, usually cross entropy is used as a loss function. So it basically outputs a higher value if the predicted class label probability is low for the actual target class. So this is a loss function, one of the loss functions, cross entropy, that can be used. There are several loss functions that can be used. So you see, in artificial neural networks and convolutional neural networks, the main difference is of the convolutional layers. Even in the conventional neural networks, ANNs, we do pooling. Sometimes we do pooling, and we get the results through cross entropy or loss functions, But the main difference is that of convolutional layers, and those convolutional layers are basically explained here. So what will happen is, first of all, we'll have convolutional layers. Then we need to understand what a stride and padding is in the convolutional layers. After the convolutional layer, we'll have a pooling layer, and pooling could be based on the average pooling as well as it could be based on the max pooling. Max pooling is more commonly used. And then we can have stochastic pooling as well. Of course, we'll have an activation function either before or after the pooling. And then we'll have fully connected layers, which will help us learn. And these layers can be governed by the backpropagation algorithm. These can be governed by those as well. And then we can have dropouts, not necessarily, but dropout layers can be there. If we have a risk of overfitting, then we can use dropout layers. And at the end, we get the loss function using the cross entropy. And that's pretty much it of how convolutional neural networks work. Of course, this is nowhere even near to what convolutional CNNs can do, because we just discussed a 2D data. Convolutional, we have discussed convolutional of just 2D. We did not yet discuss convolutional in the third dimension or in the fourth dimension for that matter, when the feature size is in 4D. But convolution in 4D can be done, in 3D can be done, which can be reduced. We call it flattening process, in which we reduce it to 2D and then to 1D, and then we do the classification procedure. So that's pretty much it from my side. If you have any questions, you're most welcome to ask.
Okay, I think that's all for the CNN part of this course. So is there any question from the audience? Ada pertanyaan mungkin dari teman-teman mahasiswa atau teman-teman partisipan yang lain terkait dengan CNN? Saya pikir CNN ini salah satu core dari deep learning ya. So CNN is one of the core concept in the deep learning. So if you have any question, so please raise your hand or just open your mic. Okay, one question from Mas Riza Setiawan. Okay, so please.
Thank you, sir. I would like to ask, in convolutional layer, can we have the feature dimension only reduced by one? So for example, the input is 5 by 5 dimension. Can we only reduce it to 4 by 4?
Mm-hmm. Okay, so do you get the question, Dr. Noman?
Yes, yes, I got the question. So yes, we can do that. For example, in this case, in this particular case, if we use a filter of 2 by 2, this is 5 by 5 image, but we use a filter of 2 by 2, then we'll get a 4 by 4 feature. Not this one. In this one, we have a stride of 2, the previous one, in which we had a stride of 1. Yeah, this one actually. So what we do is we use 2 by 2 filter, just this filter. Forget about this thing. So it will be here 2, here 3, and here 4. Similarly, 1, 2, 3, and 4. So what we'll get is 4 by 4 at the output. This can be seen from this formula as well. So if you see this formula, just a moment, this one. So what you can do is, if you want the feature size to be 4 and your image size is 5, you can set the kernel size to 2. Because if this will be, if the image size is 5 and the kernel size is 2, what you get here is 3. And 3 divided by stride of 1 is 3. 3 plus 1 is 4. So your feature size will be 4. So image size is 5 and feature size is 4. So yes, it's pretty much possible. We can do it. I hope this is the answer.
Okay, already answer, Mas Riza?
Yeah, thank you very much, sir.
Okay, you're welcome. So is there any question for other audience or other participants? Mungkin ada pertanyaan dari teman-teman? So kalau nggak ada, saya mau nanya juga. So I would like to ask to Dr. Noman.
Sure.
So despite the implementation of CNN in the image processing or image recognition, what other else of the field that we can make use of the CNN?
Primarily CNNs were built for image classification. Mm-hmm. However, we can apply it on time series as well. Any kind of data, for example, natural language processing, handwriting recognition, etc., etc. You see, even for time series, this would be a feature vector. Instead of the pixel values, this would be a feature vector, which could be, for example, in case of brain signal processing, on x-axis, this axis, we could have different channels, and in this axis, we could have time. So different time, different values of time at different channel will give us the output values. So this would be actually a feature vector based on. Just a moment, please. Someone was knocking my door.
Okay.
Okay, sorry. So you see, this would be the time, and this would be the channels. So the time series can also be inculcated in this, and we can apply similar procedure. So originally they were developed for image processing. However, they can be used on time series and every kind of application. Like, brain signal processing, we have been using it as well.
Okay, that would be great. So maybe we have some temporal and the spatial data, and we can also make use of the CNN also, right?
Absolutely. I was not using these words because I thought, they might not be available of the temporal and spatial data, which is available in the main regions. But if the students are, that's exactly the right word to use it. The spatial data, because of the channels, and the temporal data, because of the time, can be used here. Absolutely. Well explained.
Yeah. Okay. So is there another question from the audience? Okay, Mas. Okay, 2 participants. That would be great. Very great. Mas Putu Rama, silakan.
Okay. Mr. Norman, there are some things I don't understand. I understand how CNN works and CNN can reduce features, but I'm confused why we need to use CNN. As I thought is by using CNN, we are actually changing the information from the original image, especially if the result from CNN is the same size as the original image. Why don't we just the original image?
Okay, good one. That's a very valid question actually. You know, one of the main reasons of using the convolutional neural network is simplicity. So we want to actually use a lots of when we use conventional features or the pixel values directly, what we do is we lose lots of spatial interaction between the pixels, and then there is no mask applied on it as well. So one of the reasons we use CNN is that we can have spatial interaction of the the original image. What is one pixel in relation to other, or how much the other pixels are contributing in that particular region is actually incorporated in case of convolutional neural networks. So convolution gives us the interaction between the features, and of course the other main important benefit is that we reduce the size or downsample it. So if we are not downsampling it, then we are making use of one feature of CNN but not making use of the other feature. And then what we can do is we can extract multiple features using CNN. So in case of conventional features, we just have these features available, what we have, these. But in case of CNN, we can apply different masks, we can apply different strides, we can apply different paddings to get different type of features of the same image or same data, which would give us, a more richer information about that particular region, which can be used for classification later on. I hope this is the answer.
Okay, already answered, Mas Puturama?
Yes, already answered. But I have one more question.
Oh, okay.
How do we make a good max or kernel? Because if the values of all kernel is 0, then it become all the result is 0.
Yeah, that's an excellent question as well, and a very basic one. We usually use pre-built masks or filters. These masks have been built for image classification. I mean, they're quite well known. What they do is they have been built in such a way that they try to gather the maximum spatial information in that region. Usually, you might have heard about the Roberts mask, the Canny's mask, etc. Those masks are used for what? The segmentation or line detection. Yeah, the edge detection. So similarly, for edge detection, different kind of masks can be used for different purposes. Different kind of masks are available and can be used. Those have been developed already, and we use those in research. And those have been developed based on particular applications in such a way that this serves the purpose. So I told you when I was giving the lecture that usually we don't do research on what else to add in the feature, in the filter, sorry, because that area is quite saturated and we don't have much more to do in that. We just use them and gather more and more information and use it for classification. I hope this is the answer.
Okay, so already answered, Mas Puturama?
Okay, thank you, sir.
Okay, welcome.
Most welcome.
So maybe it will be the last question from Mas Ihsan. So please.
Baik Pak, izin bertanya Pak.
In Indonesia?
Yes, iya Pak.
Okay, yeah.
Oke, ketika kita membentuk suatu feature itu kita mengalihkan image dengan filter atau kernel Pak. Nah itu kan ada stride dan padding tadi kalau saya dengar gitu. Nah, stride dan padding itu kan ada nilainya tuh. Bagaimana kita menentukan nilai stride dan paddingnya Pak yang tepat, atau kita perlu mencoba-coba gitu nilai stride paddingnya?
Yeah. So one question is, how can we determine the good value for stride and padding?
Sorry, please go again.
Okay, how can we determine the value of the stride and padding? Is it kind of hyperparameter that we can try and error or something like that?
Okay, I'll tell you. It depends on what do we want to do. For example, embedding is usually done when we want our feature vector to be of same size as of image. If we want it to be same size, and the feature is coming out to be 3 and the image is 5, then we add one layer of padding and then we apply the same filter, we get 5 as the feature. We saw that in an example here, you see. So that depends on this. And stride is usually changed. The value of stride is usually changed to get different features. We can get different features from the same data. If we use stride 1, we get another matrix. If we use stride 2, we get another matrix.
Right,
so those different features can be utilized for classification. We cannot certainly tell that for a specific application, stride 1 is more important or stride 2 is more important. But we can use both of them together as well for classification. So we have more rich data if we have different strides, and we can use those for classification. I hope this is the answer.
Yeah, okay. Sudah menjawab Mas Iksan?
Baik Pak, terjawab Pak. Terima kasih.
Okay,
Pak.
sure. Thank you very much. So I think we already reached the 5 p.m. So I think it will be end of this session. So don't worry, we will still meet Dr. Noman Naseer at maybe October 21st. So around 5 or 6 weeks from now. And for the next week, the participant will meet with Dr. Novanto Yudhistira. So again, I would like to say thank you very much for Dr. Noman Naseer for your kind presentation and your Q&A session. That would be very, very great for our students. So
most welcome.
I also say thank you very much for all the participants for your eager and kind questions. It makes this course very, very warm and doing well.
Absolutely.
Yeah. Okay. So maybe that's all for this course for today. So I would like to close this session. And Assalamualaikum warahmatullahi wabarakatuh. So see you in the next week.
Okay. Waalaikumsalam warahmatullahi wabarakatuh.
Okay. Thank you, Dr. Noman. Thank you very much. Thank you very much.